In this lesson, we're going to look at lots of different functions, and we're going to look at the shape that specific functions take on. This first function here is a square root function, and without making a table of values, if I were to graph a square root function, it would start at the origin and continue up slowly as we go to the right. And it starts at the origin because the x value of 0, if I plug in here, will give me a y value of 0. And if I go to an x value of -1, I can't do the square root of -1. So I'm not going to have any x values that are on this side of the graph. So looking at this shape for this square root function, we're going to look at different things that we've talked about over the last few lessons and kind of describe all of these things in regards to this function. So first of all, the domain. The domain is where we see x values on our graph. So I have x values on this side of the graph. So all of my x values are positive or 0, no negative x values. So my domain is the x values that are greater than or equal to 0. And the same thing for the range. If I look at my y values here, I only have y values above the x-axis. So all of my y values are positive or 0. So the y values for the range are also greater than or equal to 0. I can easily see x-intercepts. It intercepts here at the origin or at the point 0, 0. And looking at symmetry for this function. So they want to know if it's even, odd, or neither. If it's an even function, I'm going to reflect points over the y-axis. And I don't have any x values on this side of the y-axis, so it is not even. If it is odd, we're going to reflect values over the origin. So if I have this point here, I would expect to have another point down here on my graph, which isn't there, so I'm just going to mark an X. So it's not either or even or odd, so it's neither one. Increasing or decreasing. So if I'm reading this like a book and I'm starting here, my y values are increasing as I go from left to right. So the function, if we just look, it's going upward from left to right. So this is an increasing function. So we'll just circle that here. And it's increasing only from 0 to infinity. Okay, starting at 0, and it includes 0 to infinity is where the x values are that is showing that the graph increases. And the maximum or the minimum is just the highest or lowest y value that we see. Because my y values, as I keep going into larger x values, my y values keep getting bigger. And when the x values are larger and larger and larger, the y values are going to increase. So there is no maximum value that the y values can hit. So there's no maximum, but it does have a minimum y value, and that would be at the y value of 0. The next graph or equation or function is a cubic function. And this is, actually it's a cube root function. So this is kind of like a slow increase, and it gets to 0, and then it keeps going up and up and up, but ever so slightly. All right, so here, if I'm listing the domain, I would have any x value give me a y value. So my domain is all real numbers. And same thing for my y's. It looks like it levels and plateaus off, but it would keep going down and down and down the farther our x values get on either side. So our range is also the set of real numbers. X-intercepts. Again, it crosses the x-axis at the origin, so it's at the point 0, 0. If I check for symmetry, an even function, it would have a point reflected over the y-axis. So I don't have any points over here, so that's not even. An odd function will reflect that point over the origin. So it looks like if I reflect this point over the origin and this point over the origin, it looks like those points are reflective over the origin. So in this case, we're going to say that our function is odd. If I start from left to right and look to see if it's increasing or decreasing, my y values are always getting bigger. Okay, even over here, they're getting bigger, although it's kind of leveling off, but it just means that the y values are getting bigger kind of slowly. So this is always increasing. There is no part of this function that is going downhill if I look left to right, and there is no maximum or minimum. Okay. The next function is an absolute value function, and we've looked at these before, like in Algebra 2 and Algebra 1, and we know that the absolute value function makes a v. The domain of an absolute value function is any x value. I can put any number in for x and get a y value. So there's no restrictions here. So my domain is all real numbers for x. And my range, if I look at my y values, I don't have any y values down below the x-axis. So my y values start at 0 and go higher. So my range has y values that are greater than or equal to 0. X-intercept is still at the origin. To check for symmetry, an even function would reflect over the y-axis, and it looks like these points do. I could take this whole part of the function and fold it on the y-axis, and it will overlap with the other side. So this is an even function. Now to check for increasing or decreasing, if I look at this part of the function, reading from left to right, it's going downhill. And then it hits this vertex and it changes direction and it's going uphill, so it's increasing. So I have part of the function that is decreasing, and that would start with x values at -infinity, and it would go all the way up to 0. And the point 0 is on the graph, so we're going to give it a closed interval, a bracket instead of a parentheses. So it's decreasing on this side, and then once I hit 0, it starts to increase. So the function is increasing from 0, and it includes 0, to +infinity. The reason I don't put a bracket around the infinities is because you don't have an ending point. It keeps going on and on and on. So there isn't a finite point to put the bracket around. And if we look at here, I don't have a maximum value up here, but I do have a minimum value, and that minimum value happens at y equals 0, or at the point 0, 0. On the next page, and I pre-wrote some graphs in here, and I kind of tried to space them out so they don't get all jumbled together. But we have lots of different types of functions. Okay, there's lots of names here, and we're going to look at what the function notation looks like for those, and we're going to look at a general graph. Now, these are parent functions because these are the most basic way we see the function. All right, so nothing is being added or multiplied or subtracted from or square rooted to the original function. Okay, so just the basic function. The first one is a constant function, and that we can represent by y equals a. And a is just any number. Okay, the number there that doesn't change, it stays the same all the time, and that would be the y equals a line, which would be a horizontal line. The next one is the identity function, and the identity function is the line y equals x. And on my graph, I have every y value and the x value being equal. So if I just make a chart, if x is 1, y is 1. If x is -3, y is -3. And if I plot over 1, up 1, that's x is 1, y is 1. If I go over 3, down 3 for -3, -3, that's going to be somewhere down here. And any point on this line right here will have the x and the y values being the same. A square function, for example, y equals x squared, and oftentimes we call this a quadratic function, will take the shape of a U. Okay. And it will have a vertex at the origin, okay, and it has a U shape. We call this a parabola. Some of these graphs do have special names, so this one is a parabola. The next one is a cube function. That means the y is going to equal the value of x cubed. And what happens here is if I start with some x values that are low, it's going to start off increasing, but increase very fast. And the same thing if I'm going downward. It's going to increase very fast. And a lot of people call this a chair function because it kind of looks like somebody could sit in this chair. Kind of takes on that shape. The square root function. Y equals the square root of x. And we looked at that on the other side of this paper, or the first page that we did. And the square root function starts at the origin and goes up and increases slightly. Doesn't increase very fast like the cubic function does. The cube root function looks kind of like this chair function, but turned to the side. So it goes up kind of slightly here, and once I hit 0, it goes up a little faster, and then it's still going up, but by very small amounts. Okay. This is the cube root function. Y equals the cubed root of x. A reciprocal function. Y equals, and we think of the reciprocal, is 1 over x. This one is kind of special because it actually has 2 parts to it. We have a branch here, and it doesn't touch the axes, but it gets very close to them. And then we have a branch here that kind of does the same thing on this opposite side. If we were talking about reflecting, this would be an odd function because it reflects over the origin. Okay, so there are 2 branches, and each branch comes very close to the axes, but it never touches, and those are called asymptotes. Absolute value function, y equals the absolute value of x. We talked about that. We know it's a v. And this one we don't see very often, but it's called the greatest integer function. And integer is a key word here. Integers are just the numbers 1, 2, 3, or -1, -2, -3, but it doesn't include space between. So the integer function would just be the points. Okay, so integer is points only. And I'm going to add a little bit to this because there's also a function called a step function, which starts with integer values, and it includes the numbers in between until you get to the next integer, and then you have an open circle. And then you move up and you have a closed dot on the integer and over to the right until you get to the next integer and there's a closed circle. Okay, so this is called the step function. Okay, so this is just showing you that each integer, it goes up, but it's not a continuous function. It's just kind of like a break. And this is just showing us that our y values are only integers. Okay, moving along. In this next section, we talk about piecewise functions. And piecewise functions are graphs that are in more than one piece. Okay, so this would be a piecewise function, P-I-E-C-E. And we can look at an example of one down here. So this is saying for our function, if the x values are between -1 and 1, it's going to have a function that looks like this. If x equals 1, the y value is 2. And if x is greater than 1, the y values are squared. Or if x is greater than 1, I square those values to get y values. So if I think about my 3 different pieces here, if I have numbers between -1 and 1, for example, -1, 0, 1/2, and let's do 1, even though I know that it doesn't equal here, but it's going to be a boundary and we need to know where that is. So if my x values are these, my y values, I need to plug these in. So I have the opposite of -1 is +1, plus 1 is 2. The opposite of 0 is 0, plus 1 is 1. The opposite of 1/2 is -1/2, plus 1 is +1/2. The opposite of 1 is -1, plus 1 is 0. So if I were to graph these points, and notice all of these are less than or equal to +1, this will give me a shape to look at for this interval. So if I plot the points, -1 up 2, over 0 up 1, over, if this is 1, over 1/2 up 1/2, over 1 up 0. All right, now it doesn't say equal to 0, so I'm going to have an open dot at over 1 up 0. So I start at -1, close dot because it's equal, and I'm going to connect my points until I get to the end of that interval, but it's not equal to, so I keep a closed dot. Now in this function, if x equals 1, then y has to equal 2. So the point 1, 2 is on our function. So over 1 up 2, here's the point y equals 2. Then from here, numbers greater than 1, okay, so that could be 2, 3, 4, but it could also be 1.1, 1.2, 1.5, 10/9. Those are all numbers that are greater than 1. So I'm going to plug in 1 into my function and pick some other numbers that are greater than 1. All right, so I'm going to pick 1, and then numbers that are bigger, 2, 3, I could do 4. But I know I'm going to square these numbers, so that would be kind of large. So if I square 1, I get 1. If I square 2, I get 4, and 3 is 9. If I plot these points, I have the point 1, 1, over 1, up 1, which is right here. This is over 1, up 0, and over, yes, this is 1, 1 right here, sorry. And then I have the point 2, 4. 1, 2, 3, 4. Then I have the point 3, 9. So 4, 5, 6, 7, 8, 9. So from here, it's kind of making a parabola and kind of going upward. Oops, I did that from the wrong spot. So it's kind of going up like this. Sorry about that, that looks messy. But we've got the arm of a parabola on this side. Now, they're asking us to use this graph, and oh, I'm sorry it's messy, to find the values of 0. So the x value is 0. I need to figure out which domain that falls into. And in this case, 0 is between -1 and +1. So this is the function that I will use to find f of 0. So f of 0 is the opposite of 0 plus 1 equals 1. I have f of 1, and I'm going to go up here. +1 is equal to, in this domain, and if x equals 1, y has to equal 2. For f of 2, I plug in 2 into the numbers that are greater than 1. So I plug in 2 into this function. 2 squared is 4. So now I'm looking for the domain. And if I look here, all of my x values start at -1, and they continue, and even +1 has a value on this function, and it continues to infinity, because I could put the number 49 in, that's greater than 1, and square it and get a number. So for my domain, my x values have to be greater than or equal to -1. I don't have anything over here that's to the left of -1. All right, so we did do the graph, and using the graph to find the range, all of my y values are above the x-axis. So for part D, my range will be the y values greater than or equal to 0. And that's it. That's what the piecewise functions are. And for these, work little bits at a time on your graph, and I would suggest picking a few points, 2 or 3 points from each interval, except for this one if it's equal. This is just a single point, but these have extensions to those points, so they definitely cover an interval. So get a few points and plot those and see what works. And again, I'm kind of sorry that was a little messy.